This is the first module of chapter 9. The chapter 9 is devoted to the numerical solution of partial differential equation. Again, the partial differential equation is a very important tool to solve many real life problems, appears in mathematics, physics and different branches of engineering. A lot of methods are available to solve partial differential equations, but here we consider only finite difference method to solve partial differential equations. In this module, that means in first module, we consider parabolic partial differential equation. First, we consider the second order partial differential equation, and the general form of second order partial differential equation is shown in equation 1. Here a into del 2 u del x2 plus b into del 2 u del x del y plus c into del 2 u del y2 plus d into del u del x plus e into del u del y plus f u equal to g. This equation can also be written in this form, that means in terms of suffix or subscript of u, where a, b, c, d, e, f and g are the functions of x and y. The second order PDEs are of three types. The first one is called elliptic type, second one is hyperbolic type and third one is parabolic type. So, all second order partial differential equations can be divided into three groups. One is elliptic, other is hyperbolic and other is parabolic equations. The type of a PDE can be determined by finding the following discriminant, which is defined as delta equal to b square minus 4 into a and c, where a, b, c are mentioned in equation 1 or 2. So, depending on the values of delta, we can classify the second order differential equation, partial differential equation. If delta is less than 0, then the PDE is called elliptic. If delta is equal to 0, then the equation is called parabolic, and if delta is greater than 0, then the PDE is called the hyperbolic. So, depending on the delta, we can classify the second order partial differential equation. Now, we consider three types of partial differential equation. The first one is elliptic equation. The most simple example of this type of PDEs are Poisson equation. This is defined as equation 3, as in equation 3. This is two-dimensional Poisson equation. Note that the right hand side g is a function of x and y, this is a given function, and another kind of elliptic equation is Laplace equation, and in this equation the right hand side is 0. That means the Poisson equation and Laplace equation are almost similar. When g is equal to 0, then Poisson equation nothing but the Laplace equation. The analytic solution of an elliptic equation is a function of x and y. Obviously, it will be a function of x and y, and the solution must satisfy the partial differential equation at every point within the region R where the equation is defined, and it is bounded by a plane closed curve C. Also, the solution must satisfy the sum condition at every point on the boundary C. So, these are the sufficient conditions for a solution of equation 3 or 4. The condition that dependent variable satisfies along the boundary curve C is known as boundary condition. Now, we consider parabolic equation. The most simplest example of parabolic equation is the heat conduction equation, which is of the form written in equation 5, that means del u del t equal to alpha into del 2 u del x2, where alpha is a parameter, t represents time and x represents the space variable or length along the conducting space. In this equation, the time t is involved as a independent variable. The solution u represents the temperature at a distance x from one end of the thermally insulated bar after t second of the heat conduction. So, this is a physical problem. U represents the amount of heat that was spread along the x direction at a particular time instant t. In this problem, the temperature at the ends of a bar are known for all time. That is, the boundary conditions should be given to solve this equation. Now we consider hyperbolic partial differential equation. In this case also, the time t is involved in the equation. The most simplest example of hyperbolic equation is the one-dimensional wave equation. This is the simple form of the wave equation. That means left hand side is del 2u del t2 equal to c square into del 2u del x2, where t represents time and x represents the length. In this case, u is the transverse displacement of a vibrating string of length L at a distance x from one end after a time t. Hyperbolic equations generally originate from vibration problem. The values of u at the ends of the string are generally known for all times, that means the boundary conditions are known, and the shape and the velocity of the string are given at initial time, that is the initial conditions are known. That means if the boundary conditions and initial conditions are given, then we can solve the equation 6. I have mentioned that the partial differential equation can be solved with the help of finite difference method. So for this purpose, we divide the entire xy plane into sets of equal rectangles of length delta x equal to h and delta y equal to k by drawing some equally spaced grid lines parallel to the coordinate axis. That means the x direction is divided into some intervals with space h, and y direction is divided into some other number of intervals with spacing k. That is, xi is equal to ih and yj is taken as equal to jk, where I equal to 0, plus minus 1, plus minus 2 and so on, j is equal to 0, plus minus 1, plus minus 2 and so on. In this case, x0 and y0 are taken as 0. The intersection of horizontal and vertical lines are called the mesh points, and the ijth mesh point is denoted by xi comma yj or ih comma jk or simply ij. The value of u at this mesh point is denoted by uij, that is uij means u at the point xi comma yj, and which is equal to u at ih comma jk. Our problem is to find the values of u for different mesh points. The approximation of first order derivatives, first order partial derivatives in terms of central difference approximation or other difference approximation. The first order partial derivative with respect to x, that means del u del x, is approximated as ui plus 1 comma j minus ui comma j whole divided by h plus order of h. So this is the forward difference approximation. Note that the subscript of u, the second subscript of u is j remains unchanged, and the first subscript is changed because the partial derivative is taken with respect to x, that means with respect to the first variable. For this reason, the first subscript is changed and second subscript remains unchanged. This is the backward difference approximation of del u del x. This is the third representation, that means the last representation is nothing but the central difference approximation of del u del x. In this representation or in this approximation, the order of error term is h square. Similarly, del u del x can be approximated with the help of forward difference approximation that was represented by equation 10. This is backward difference approximation and this is the central difference approximation. Note that the central difference approximation gives the better answer than the forward and backward difference approximation. The second order partial derivatives are approximated as, this one is the approximation of del 2u del x2, this is the central difference approximation, and this is the approximation for del 2u del y2. And note that in this approximation the truncation error are of order h square and order of k square. Now we consider the parabolic equation, and this equation is to be solved by finite difference method. Let us consider the following parabolic equation known as heat conduction equation. This is the simplest example of parabolic equation we have mentioned in previous slide. The differential equation is this one, del u del t equal to alpha del 2 u del x2 with the initial condition u x 0 equal to f x, that means when t equal to 0 u is equal to f x, and the boundary conditions are u 0 comma t equal to phi t and u 1 comma t equal to psi x. That means the left bound is x equal to 0 and the right bound is x equal to 1. Now we approximate the given PD, parabolic partial differential equation, by using the finite difference approximation for del u del t and del 2 u del x2 defined in equations 10 and 13. So using this approximation, the equation 15 reduces to equation 16. After simplification, we get the following equation: ui comma j plus 1 equal to r into ui minus 1 comma j plus 1 minus 2r ui comma j plus r into ui plus 1 comma j, where r equal to alpha k by h square. Alpha is the given constant, h and k are the step length along x and y directions. So r is the given r is the very important parameter for this equation. So for this formula, one can compute the value of u at the mesh point I comma j plus 1 when the values of ui minus 1 comma j, ui comma j and ui plus 1 comma j unknown. These three values are present in the right hand side of equation 17. So if these values are known, then we can calculate the value of ui comma j plus 1 from equation 17. So for this reason, this method is an explicit method. By stability analysis, it can be shown that the formula gives a stable solution if 0 strictly less than r less than or equal to half. So if this condition is satisfied, then the equation 17 gives the stable solution for the parabolic equation, particularly the heat conduction equation. This is the diagrammatic representation of meshes of heat conducting equation. The known values are denoted by the field circle and unknown values are denoted by the circles. The initial values are given along the x axis and the left boundary values are given along the t axis and right boundary values are given along the right vertical line. Our problem is to find the value of u for each mesh point at each mesh point, which are the intersection of the horizontal and vertical lines. Also, it is mentioned that the values of ui comma j plus 1 can be determined if the values of u at I minus 1 j, I comma j and I plus 1 comma j, if these three values are known, then we can find the values of ui comma j plus 1. These 4 points are mentioned within the diagram along the jth row and j plus 1 row. Now we consider one example to illustrate this method. Basically the method described in these previous cases. This method is the explicit method. So we solve this equation by using the previous explicit method. In this case the boundary conditions are 0 and 3t and the initial condition is u x comma 0 equal to 1.5 x. To solve this equation, we assume that h equal to 0.2 and k equal to 0.01. Therefore, the value of the parameter r equal to k by h square, in this case alpha is 1, so r equal to k by h square, which is equal to 0.25 and it is strictly less than half. That means the scheme gives the stable solution for heat conducting equation. So, this diagram represents the boundary conditions and the initial conditions for the given problems. The red column represents the left boundary conditions and the right column represents the right boundary values, and the first row within the table represents the initial values of the variable u for different values of x and t equal to 0. Using the finite difference approximation, that means del u del t is given by the central difference approximation, and del 2u and del x2, del 2u del x2 is given by the central difference approximation. The given PD reduces to this equation: u I comma j plus 1 equal to 1 by 4 u I minus 1 comma j plus 2 u I comma j plus u I plus 1 comma j. So, this equation gives the values of u for different values of I and j. From this equation we get u11 equal to 0.3, u21 equal to 0.6 and so on. So, using this technique we fill up the entire table. That means this table gives the values of u for different values of x and t. For example, the value mentioned in red color, that means the value 0.50125 is the value of y when x equal to 0.4 and t equal to 0.05. Similarly, 0.56968 represents the value of u when x equal to 0.6 and t equal to 0.5 and so on. So, this table gives the values of u for different values of x which is mentioned along the horizontal line and for different values of t mentioned in the vertical line. An explicit method is described to solve parabolic equation, particularly heat conduction equation. This method is very simple, but this method has a limitation. That means the method is applicable if the value of the parameter r satisfies the condition 0 less than r less than equal to half. Now we describe another method known as Crank-Nicholson implicit method. This method gives better result than the explicit method. Crank-Nicholson implicit method to solve parabolic equation. This method is developed by Crank and Nicholson in the year 1947. This method reduces the total computation time. Also, this method is applicable for all finite values of r. In this method, the given PD is approximated by replacing both space and time derivatives by their central difference approximation at the midpoint of the points IH, jk, that means the mesh point ij, and IH, j plus 1 k. That means at the point IH, j plus half into k. So, this is the middle point of these two mesh points. So, the right hand side of the equation is approximated at these 2 points. The given parabolic equation is divided into 2 parts, that means the right hand side of the PD, that means the term alpha into del 2u del x2 is divided into 2 parts. The first part is approximated at the mesh point ij and the second part is approximated at the mesh point I, j plus 1. So, this is the new concept appeared or posed by the Crank-Nicholson method. Thus, using central difference approximation, the above equation reduces to this form. After simplification, the above equation reduces to equation number 19. Note that in equation 19, there are 3 values of u present in right hand side and 3 values are present in the left hand side. And in this case, the value of r equal to alpha k by h square and the value of j are 0, 1, 2 and so on, but the values of I are 1, 2 up to n minus 1, where n is the number of subdivisions of x. In general, the left hand side of the above equation contains 3 unknown values, but the right hand side has 3 known values of u. So, this is an implicit method. For j equal to 0 and I equal to 1 to n minus 1, the equation 19 generates n simultaneous equations for the unknown u11, u21 up to un minus 1, 1. That means these are the values of the first row of the table. In terms of the known initial values, u10, u20 up to un minus 1, 0. And the boundary values are u00 and un0. So, depending on the initial values and boundary values, we can calculate the values of u11 to un minus 1, 1. Thus, for this problem, initial and boundary conditions are required. Without both these conditions, we cannot solve the given parabolic equation by Crank-Nicholson implicit method. Similarly, for j equal to 1 and I equal to 1 to n minus 1, we obtain another system of equations containing the unknowns u12, u22 up to un minus 2 in terms of the known values obtained in previous step. Thus, for each value of j, where j equal to 2, 3 dot dot dot, there is a system of equations. Now, by solving this system of equation, we can find the values of u for different mesh points. This is the diagrammatic representation of Crank-Nicholson implicit method. Here also the field circle represents the known values, that means the initial values, left boundary and right boundaries are given or known, and the circle position represents the unknown values of u. And from this diagram we see that if the three values at level j is known, that means the three values at level j are known, then we can calculate the three values at level j plus 1 using the Crank-Nicholson implicit scheme. The system of equation 19 for a fixed j can be expressed as a following matrix notation. This is the matrix notation. This is a system of equations. Obviously, it is a tridiagonal system of equations for a particular j. And the right hand vector, that means the values of d1j, d2j, etc. up to dn minus 1j are calculated by the following three equations. Now, we consider one heat equation to solve by Crank-Nicholson implicit method by taking h equal to 1 by 4 and k equal to 1 by 8 and 1 by 16. Here the boundary conditions are u0t equal to u1t equal to 0 for any positive t, and the initial condition is ux0 equal to 3x. First we consider h equal to 1 by 4 and k equal to 1 by 8. So, in this case the value of r equal to k by h square, which is equal to 2, and we mentioned that the Crank-Nicholson method is applicable for all values of r. The Crank-Nicholson iteration scheme is given by these equations. The initial and boundary conditions are shown in the following figure. So, in this case we have to determine the values of u at the mesh point A, B and C. The boundary conditions are mentioned by field circle, initial conditions are also mentioned by the field circle. We have to determine the values of u at the point A, B and C. The initial and boundary values are given by these expressions. The unknown meshes are A, B and C for different values of I and j mentioned adjacent to the point A, B, C, and for this case the system of equation is this one. And after substituting the values of u00, u10, u20 and u30, u40, we get the following system of equations. So, by solving this equation we get the values of u11, u21 and so on. Note that this is a system of tridiagonal equation containing three variables and three unknowns. The solution of this equation is u11 equal to 0.60714, correct up to 5 decimal places, u21 equal to 1.07143, u31 equal to 1.10714. Now, u31 means the value of u when x equal to 0.75 and t equal to 0.125. So, using this technique we have determined the values of u for different mesh points. Now, we consider second case. In this case we assume that h equal to 1 by 4, but we consider k equal to 1 by 16, that means the value of k is taken as 1 by 16. In this case the value of the parameter r is 1. So, the Crank-Nicholson scheme is this one, and this is the boundary and initial condition and the other unknown mesh points. So, in this diagram we see that the values of u are to be determined for the mesh point A, B, C and the mesh points B, D, E and F. So, first we calculate the values of u for the mesh point A, B, C by generating a system of equations, and depending on these values we calculate the value of u at the mesh points D, E and F. So, for the initial values are u00 equal to 0, u10 equal to 0.75, u20 equal to 1.5, u30 equal to 2.25 and u40 equal to 3. And the boundary conditions are u01 equal to 0, u41 equal to 0, u02 equal to 0 and u42 equal to 0. And for r equal to 1, the middle terms of the right hand side of Crank-Nicholson equation becomes 0. So, for this case the system of equations are, these are the three equations, and these three equations determines the value of A, B, C, that means the values of u at the mesh point A, B and C. After substituting the values of the initial and boundary values, we obtain this system of equations, and by solving this equation we get the value of u11, u21 and u31. So, these are the values of u at different mesh points. Now, depending on these values we can find the value of u at the mesh point D, E and F. Again the Crank-Nicholson equation for the mesh point D, E and F for different values of I and j are respectively these three equations. After substituting the values of u appears in the right hand side of the equations, we get the following three equations. The solution of this system of equation is u12 equal to 0.52041, u22 equal to 0.79592, u32 equal to 0.52041. So, these are the values of u at the mesh point D, E, F. That means the Crank-Nicholson method is used to solve the values of u at the mesh point A, B, C, and in second step we have determined the values of u at the mesh point D, E, F. In this module, two methods are described to solve parabolic partial differential equation. The first method is an explicit method. This method is simple, but it has a limitation. That means the parameter of this method must satisfy the condition 0 less than r less than or equal to half. But the another method known as Crank-Nicholson implicit method, that method is more better than the explicit method because this method gives more better result and takes less computational time. Also, this method is applicable for all values of r.